OK， 来，我们做，我们继续啊，第二题。Okay, number 2, water in an ice maker of a refrigerator has a mass 0.4, temperature. This is the initial temperature. What is the temperature of water after this amount of heat has been removed? You see heat removed, so that is a cooling. What happens in cooling process? Temperature drops. Remember this too. Okay. Now, what I want to find is the final temperature. If this is the initial temperature, 22, the final must be lower than it, right? Because it's cooling, right? So using the same formula, Q mc delta T, Q is 33600 equals to 0.4 into, okay, water, right? So water is 4200. Specific heat capacity, water 4200 times into the change in temperature. Okay, this one I leave it first. I want to find this. So I got 33600 equals to, okay, 1680 times change in temperature. And this one I get 20 degrees Celsius. The change is 20 degrees Celsius. Now remember, change can be increase or decrease. In this case, is it increase or decrease? That's why you should know it is cooling or heating. That's the reason, because you want to know this one is increase or decrease. So this is decrease, right? So initial temperature is 22. It has decreased 20. So we minus 20. Then we get 2 degrees Celsius. This is my answer. That is my final temperature. Okay, example 3. Mechanic drop a steel nut of mass and temperature 90 into water. Okay, let me highlight this too. We got two objects here, steel nut, this one and this one, and water, this mass and this temperature. What is the temperature when the steel nut and the water have come to thermal equilibrium? Okay, the mechanic dropped a nut at a temperature of 90 into a water, and the water is different temperature. So when he dropped the nut inside, what happened? There's a heat transfer. So we know that the heat goes from the hotter to the cooler, right? So the heat goes from the nut to the water. Okay, now I'll do this like this. Okay, you see 0.02 kg steel nut. Let me write this down first. Temperature of 90 degrees Celsius. And then I write down the water, 0.25, water at 24 degrees Celsius. So what happened here is when these two objects are in contact, heat exchange takes place. Heat flow out from where? Flow out from the steel nut, correct? Heat flow out from the steel nut and the temperature drops. Where does the heat go? Goes to the water. So the heat is being added into the water and the water temperature rises. And they reach the same temperature after a certain period of time. And that temperature is when they reach the thermal equilibrium. Okay, it is the temperature at thermal equilibrium. We don't know the temperature here, so I'll just call it X. Okay, but I know that they reaches somewhere in between. It's always between these two. It's never beyond the boundary of this 90 and 24. Okay, it always is between this. Okay, this is when they reach thermal equilibrium. Now, before I calculate this one, before I find the x, there is one assumption, very important assumption I need to make. That is, I have to assume that the exchange of heat is between, it is only between the steel nut and the water. Okay, assume. Why I want to make this assumption? So what does this mean, by the way? Assume the exchange of heat occur only between these two, meaning that the heat is not lost to the surrounding. In reality, heat always lost because you can never have 100% transfer to another object. It's always lost to the surrounding. But in our calculation, to make our life easier, I have to make this assumption that the heat is never lost. Okay, 100% of heat from the steel nut will be transferred 100% to the water. That is the assumption I make in order to do the calculation. Okay, so based on this assumption, I can write that heat given out equals to heat absorbed. Heat given out equals to heat absorbed. Take note of this. In many of the calculation, you are going to need this, especially question that involves the transfer of heat. Okay, heat given out is always equal to heat absorbed. Given out by who? By the steel nut. Absorbed by who? By the water. Okay, so heat given out is Q, and heat absorbed is equals to also Q, Q1, Q2. Okay, so here I expand the equation. M1 C1 delta T1. This is M2 C2 delta T number 2. I know that this equals to this one. Okay, so I just put in the value. What is M1? Okay, M1 is the steel nut, 0.02 times into the specific heat capacity, 450, and times, okay, now, change in temperature, what should we put? Remember, just now in example 1, I said I don't want to deal with the negative, right? So I always take the bigger value minus the smaller one. All I'm interested is only the difference in value. So which one is bigger? I know that the steel nut, it goes from 90 to X. In the end, it reaches this X temperature, right? So whatever is the temperature of X, whatever is the value, but I know that X must be lower than 90, right? X must be lower. So 90 is definitely bigger. So I would take 90 minus X. So this is a positive value. Equals M2, 0.25 times 4200 times, again, the change in temperature, we go from 24 to X, rising. So X is a bigger number. I take the bigger, I minus the smaller one. So I don't have a negative value. Okay, so all this is positive and is balanced. So from this equation, I can find what is the value of X. Okay, calculate this. Answer is 24.56. Okay, guys, we'll take 2-minute break and we'll come back after 2 minutes and I'll continue. OK， 来，我们继续啊。Finding specific heat capacity, right? All the values that you see in the table, all the specific heat capacity values, we find it experimentally. Okay, so we find it experimentally. Now, the method we use to find the specific heat capacity, okay, let's take one example. Finding the specific heat capacity of an aluminum cylinder. Okay, so let's say I'm given a block of aluminum. Okay, so here I have a block of aluminum that I want to find the specific heat capacity. Let's say I don't know the specific heat capacity. Okay, I want to calculate it. Now I'll make a hole on top. So this part is hollow. And then what I would do is wrap the aluminium with an insulator. Okay, 可以是什么 insulator 都可以. It can be a rug, a wool, tissue paper, anything, okay, any thermal insulator. So why I want to put insulator around it is because I want to minimize the heat loss. Okay, insulator 我要 minimize heat loss to the surrounding. 因为如果有 heat loss then 我的 calculation 就不会 accurate. Now, let's say I put a tissue paper. And then underneath it, I put another insulator just to kind of add one more layer. Okay, so this one maybe I put a polystyrene. Okay, so I have double layer of insulator. Okay. Now, to find the specific heat capacity, C, what is my formula? I need to find the Q and the M and the change in temperature, right? So the M I can measure. I will measure the mass of the aluminum block. So that's okay, I know the value. The Q is the heat supply to heat the aluminum, right? Now, in this example, in this experiment, I'm going to use a electric power supply. So I will take a power supply, connect to a heater. This is an electric heater, and I put the heater inside here. Connect to the power supply, plus minus. Okay, with a known power. So I need to know the power of the power supply. Let's say it's 1000 watt. Okay, so why do I need to know the power? Because power equals to energy divided by time. Okay, so using this formula, energy equals to power times into the time. Energy is in joule, power is in watt, and time is in second, all SI unit. 所以如果我知道我 heat 它的时间加上它的这个 power rating 这样我就可以算它的 energy。可是这个 energy 是 electric energy. Okay, electrical energy, but eventually it will be converted to heat energy. Okay, so I need to know the duration that I'm heating to calculate the Q. Now that would be my Q, and the change in temperature. Initially, I have to measure the temperature of the aluminium. So I will make another hole here, and I'll put in the thermometer. Now inside this hollow space, to increase the efficiency of the experiment, I would add in oil. Add oil. The reason I do that is because I want to make sure that the thermometer is in contact with the aluminum block. Okay, they're in contact. So the transfer of heat happen quicker and they reach thermal equilibrium faster. So the temperature of the aluminum is the same as the temperature of the thermometer. Okay, so the reason I put oil is because I want to speed up I want to increase the thermal. Okay, we say that if you want to write the answer, right, if we increase the thermal contact. Okay, thermal contact. Yeah, this is the keyword. Thermal contact between the thermometer and the aluminum block. Okay, so I take the initial temperature, Ti, and then after I heat it, let's say I heat it for 5 minutes. Okay, T 5 minutes, and then I calculate what is the final temperature of the aluminum block. Then I will do my calculation. Okay, T 5 minutes, energy supplied by the heater equals to power times time. So that's 1000 watt times into 5 minutes times 60 into second. Okay, 300,000 joule of energy. This is electrical energy, right? So another assumption we have to make is that the electric energy will be converted to heat energy. Conservation of energy. Okay, we said that this 100% will be changed to 100% of the heat energy. Okay, so if the question asks you, especially the practical questions, they ask you, okay, what is the weakness of this thing? Then you can talk about the energy. This one, okay, is not, in reality, it's not 100%. Okay, the conservation of energy. You can talk about all this. So the heat energy, this one would be the Q, and so we have Q equals to the 300,000 joule, and we find the change of T, finals minus initial, and also we can find the mass. All these known values, then we can find the specific heat capacity of aluminium. Okay, so simple experiment to find specific heat capacity. Let's say I want to find the specific heat capacity of water. Then I could set up a very simple experiment, like I use a polystyrene cup. Okay, why do I choose polystyrene? Because it's an insulator, right? So to separate from the surrounding. So all the heat transfer happens inside here. Then sometimes you will see the experiment, it comes with a stirrer. Like this is a stirrer. What is the function? This one, together with the heater, right? The heater you put it inside. Okay, that's the heater. Okay, so when you heat the water inside, right? The stirrer, you have to stir, you have to constantly stir it so that the temperature is being distributed evenly throughout all the liquid, all the regions here. Okay, that's the function of the stirrer. Okay, so this is another setup: stirrer, and then heater, and also we put one thermometer. Calculate the specific heat capacity of water. So from these two experiments, we know that the Q we can get from different energy sources. Okay, this Q stands for heat energy. We can get from the electrical energy, we can get from potential energy, we can get from kinetic energy. Now, what do I mean by this? Let's say I have an object here, unknown material. Okay, 我不知道它的 material， 然后我推它去这边。So it has a speed of, let's say, 5. So suppose that this is a rough surface. So there's a friction. And when I push this, the friction will create heat. And the heat will heat up the object. Okay, so initial temperature of the object. And then after you push it here, maybe the temperature rises a bit. Final becomes hotter a bit at the base. Now, where does the heat come from? The heat comes from the friction, correct? And the friction comes from the kinetic energy. Okay, so the kinetic energy, half mv squared. This is the formula for kinetic energy. Okay, 我们看它的 mass, 然后我们乘它的 speed. You can calculate the kinetic energy in joule. Kinetic energy eventually will become the heat energy. So I can write this formula as Q equals to mc delta T. So I change this half mv squared equals to mc delta T. Then I get another formula. Okay, based on the speed that it is moving at, if I know the mass, I can find what is the temperature increase of this object. Because it's all about energy. Heat energy, kinetic energy, they are all the same. They are just energy. Okay, so one can be converted to another one. Potential energy. If you see the water at the top of the mountain, if you measure the temperature, and when it reaches the bottom, you measure the temperature again, you will find that the temperature at the bottom is slightly higher. Why? Because some of the potential energy, when it is up there, will convert to heat energy when it reaches down, when it comes down. Okay, so that's why the heat energy is used to heat up the water. So the water temperature slightly will increase. Okay, that is potential energy converted to heat energy. So we can also write the formula Q mc delta T. The Q, I can change it to potential energy mgh 等于 mc delta T. You get another one. Okay, so equation number one, equation number two, and more commonly, these two are not as common as the electricity. This one definitely will come out one. So Q equals to MCT, right? MCT. So the Q, we use the electrical energy. So PT. We take the power times the time. That is the electrical energy. So equals to MC delta T. This is equation number three. They give you the power. Okay, I take a glass of water, initial temperature at 25. I put a heater with a power of 1000 watt. I heat it for 2 minutes. What is the final temperature of the water? Can you find? Power 1000 watt. I heat it for 2 minutes. What is the final temperature of the water? Then we are going to use the PT MC delta T. This is heating, right? Heating temperature rise. Okay. Mass of water 2 kg. So 1000 times into 2 times 60 equals to 24200, and the change of temperature. Okay, change of temperature, I can just change it to, oops. I can just write it as X minus 25. X is the final. Okay, because I know X it will be greater than 25. So I take the greater minus the smaller. Okay, class. That's it for the specific heat capacity. I'll send you some exercises. You can take the time, you do it, and if you have question, you can ask here. Khảo试拍了啦。 answers at the back.